Looking at constant rates of change. So rate of change is also just known as the gradient or a slope of a line. A constant rate of change is the rate of change of a linear line because it's constant. It's always at the same slope, same speed, if you will. Okay, so a positive gradient means that as x increases, y also increases. We were to draw that on a graph, which way does a positive line go? Positive gradient? Yeah, it goes up left to right, that way. Same for a line that's not linear, actually. You can still have positive gradients. Be something like that. Although it's curved, it's still a positive gradient because as if x is increasing, y is also increasing, just by different rates along the line. Right, a negative gradient means that as x increases, y decreases. So, of course, that means that either a straight line going down, so as x increases left to right, y is getting less and less. And you can also see that in curved lines, so maybe a line that goes like that. Still the same, even though it's curved. The gradient varies at different points, but it's always negative. A zero gradient means that as x increases, there is no change in y. So that would be, is it horizontal or vertical? Horizontal, yeah. A line like that. An undefined gradient means that as y increases, there's no change in x. So that's...
Is it undefined because you divide by 0?
Dividing by...
What is the 0?
It's an undefined graph if it doesn't have a y value, I think. So that's something like x equals 3. It's kind of hard to explain. Like this one, it would be like y equals 4, which is also y equals 0x plus 4. And there's like a 0 gradient because gradient always goes in front of the x. For this one, like it's not in that same form. Like there's no y in the formula. So there's no real gradient because it doesn't follow like a y equals mx plus c kind of line. Just, you know, accept it. It's kind of hard to explain. But yeah, just the undefined gradient means that it's a vertical line. We might look it up later. I'm not actually sure. Like I've never really looked into it. I've just always accepted it. I'll just add one thing. How do we find the gradient of a line? A straight line?
Right over right.
Yep.
Oh, 1, 2 minus 1, 1.
Yeah. Oh, whoops. Gradient equals rise over run, or y2 minus y1 over x2 minus x1. So as long as you've got 2 points on the line, you can find the gradient. Yep.
Can you do y1 minus y2 and then x1 minus x2? Or does it have to be y2 or x2?
You can do that. It just as long as, because it doesn't matter like which one you label as x1, y1 and x2, y2. You could label them either way, just as long as you like put them in the right spot. Yeah. So don't do like y2 minus y1 and then x1 minus x2 because that won't work. Right, so now looking at average rate of change. So car speed is nonlinear because you're always speeding up and slowing down, stopping and traveling at a constant pace. So it's like all over the place. If you do your kilometers traveled over time, so distance over time, you'd get a nonlinear line, speeding up and slowing down. But, however, if you travel a total of 60 kilometers in 1 hour, even though you're speeding up and slowing down throughout that, you can say that your average speed or your average rate of change was 60 kilometers per hour. So it's just the average speed or the average rate of change over some time. So we've got this example here. It's obviously a nonlinear line, but we can find the average rate of change between points A and B. And it's very easy. Essentially what you're doing is just drawing a linear line through those 2 points. So I'll try to do it without a ruler, but I can't guarantee anything. Ah, nope. Let's try again. It's easy for you guys because you got a ruler, but there we go. So essentially what you're doing, yeah, meeting those 2 points up with a straight line, and then you're just finding the gradient of that straight line. I mean, you don't even have to do that. You can skip that step. You just do y2 minus y1 over x2 minus x1 with those 2 points. Nice and easy. So we get average rate of change equals y2 minus y1 over x2 minus x1. Looking at it, will it be a positive or negative rate of change?
Positive.
Good. So then just 30 minus 12 and 12 minus 2. (18 over 10). Oh, if we add in here that we're doing time in seconds over distance in meters, then you can actually think about it like the y's were on top and the y is meters. So you'd put like a meters on top, and the x is on the bottom, and x is seconds. So 18 meters for every 10 seconds. Then you can write that as 1.8 meters per second.
So you don't simplify down to 9 over 5?
You can, but you don't really, when you're talking about meters per second, you don't really say like 9 over 5, 9 fifths meters per second. Like you usually say it as a decimal, but both are right. Yeah. You can say 9 meters per every 5 seconds, for every 5 seconds.
Are we doing like meters per second?
That's the same thing.
No.
Meters over second is meters per second.
Is it? No.
It's the magnitude. It's the speed. How long is chapter 19?
I think it's the same length, so only 5 exercises, but it's a little bit harder. Okay, so now we're looking at instantaneous rates of change. So we've done constant, we've done average, and now it's instantaneous rates of change. So first we're going to look at what a tangent is. It's a linear line that touches but doesn't cross a curve at a single point, and it has the same gradient as the curve at the point it touches. Say it all again. I think it'd be better to demonstrate it with some diagrams. So say, for example, we've got our basic cubic function. I want to draw a tangent line to this point here. A tangent is a linear line, so it's a straight line that touches that point but doesn't go through it, and it's got to have the same gradient as our cubic line at that point. So we draw it in, it's going to be roughly the same gradient, so it's going to go about this way. It's kind of hard for me to draw a straight line. Yeah, it's about there. Right, so it touches the curve, doesn't go through it. It can go through it at other points, like you see if you extend this tangent, it'll go through the curve there. That's fine, but at the point it touches but doesn't cross. And it has the same gradient as the curve at that point. It's the same for those of you who do physics. If you tie a weight to the end of a piece of string and spin it around over your head, and then if you let it go, disregarding gravity and air resistance and everything, it'll fly off at a straight line. That's a tangent.
Yeah, I think we're doing that there. Not there.
So if we've got a circle function and we're drawing a tangent line to this point here, right? Touches that point, it's got to have the same gradient as the circle at that point. So if you imagine like you're going around the circle and then you get to this point and you come off at a straight line. So you're going around, 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 and then you hit that point and you go straight off it. Either way. Or if you want another example, we'll do a parabola. Parabola. And I want the tangent line, oops, at that point there. Yeah, what's the gradient of that tangent line? Yeah, it'd be zero gradient. It'd be like that. If you'll notice, like if you did tangent lines the whole way along, this is hand drawn, so it's not going to be great, but you'd have that one would be pretty close to horizontal. That one would like start coming that way. That one would go that way. The gradient of all those tangent lines, it's constantly changing when you go around the parabola or when you go around any curve. When you get to the bottom of a parabola, it's horizontal, and then you start going back up, and then it turns back the other way. There you go. That. So any point at like the maximum or the minimum of a parabola, the turning point will be zero gradient. Yep.
With the first cubic tangent, is it still a tangent even though it goes through?
Yeah, that's what we said. Like when we say do not cross, I mean doesn't cross at that point. It can cross at other places, but at the point where it meets it, it doesn't cross, it just touches. Yeah.
Touches meaning it has the same values, X and Y values.
Sorry?
Touches does that mean it has the same X and Y values?
At that point, yeah. Okay, so instantaneous rates of change is the gradient of a curve at a specific point along the line. So basically we're looking for the gradient of that straight line tangent. We already figured it out for the parabola. At the turning point, the gradient is zero. So the instantaneous rate of change at the turning point of a parabola is zero. So we can estimate instantaneous rates of change in two ways, and the key word is estimate. These are not exact ways to do it. We're only estimating at this point. So the first one is to do that, draw a tangent line at a point and try and find the gradient using like rise over run or y2 minus y1 over x2 minus x1. The other way, which is my personal fave, is you just pick 2 points on the curve that are really, really close to each other. So maybe like 0.1 away from each other or 0.05 away from each other or something like that. Very, very close. And then just use y2 minus y1 over x2 minus x1. So the closer the 2 points are, the more accurate you'll get.
So does that mean that everyone will have the same answer?
No, not everyone will have the same answer.
So what happens when you mark it?
I will take a look at what you did, and if the working out is correct, then you get full marks.
Awesome.
Okay, so find the instantaneous rate of change of y equals 1/2 x cubed minus 2x plus 1 at x equals 2.
Yeah.
So I would say, because we're not given a diagram, it's kind of hard to draw a tangent line. So use the second method, and that's the y2 minus y1 over x2 minus x1.
So then do we just sub in a random x value?
Well, not random, very close to 2.
After it's given 2.
Yeah, so like for example, when I did mine, I did 2.1. But you could go even closer and get it more accurate. 2.01 or 2.0001. The closer you are to x equals 2, the more accurate your gradient will be.
But you can't use 2.
Well, no, because it would give you the same point, and then you get the gradient 0 over 0.
Use a calculator.
Yes.
Should we draw a cubic?
You don't have to draw it.
Just random.
But you're right, it's a cubic.
I don't really get what I'm doing.
Okay, sub in x equals 2, find out what y is. Find your first point.
Is that really it?
That's it. And then sub in x equals 2.1 and find your other y.
So how do you know if you put one on the graph?
Because a cubic like that looks like, is it that one?
I don't know.
I'm pretty sure. Think back to your cubics.
Wait, we did that cubic.
Yeah, we did. A cubic in that form, like there's 2 types of cubics. There's the point of inflection form, which is the factorized version, and then there's the expanded out version, which is like a snake. And so that type of cubic keeps going. Its domain is the set of R, because it keeps going either way. Like it'll keep going down here and up here. So it doesn't matter what x value you pick, it'll always be on the line.
So you decided like 2.1.
-1.
Okay, so we're going to sub in x equals 2. So y equals,
No, it's cube not square, dude.
okay, so y equals 1/2 of 8 minus 4 plus 1. So half of 8 is 4, take 4 is 0, plus 1 is 1. So we've got the point 2, 1 on the line. Now I'm going to pick x equals 2.1. So y equals 1/2 2.1 cubed minus 2 times 2.1 plus 1. I've done this one earlier, so that's 9.261 minus 4.2 plus 1. So y equals 1.4305. So the other point you've got is 2.1 and 1.4305. Right, you've got 2 points that lie on the line that are very close to each other. y2 minus y1 over x2 minus x1.
And then do we do everything first?
No, that's it. So instant rate of change or instantaneous rate of change, I wouldn't say equals. I'd probably say, you know, that approximately. Because as we said, like this is not an exact way to find the gradient at a point. It's an estimate.
We wouldn't be wrong if we did equals, would we?
Oh, I wouldn't mark you down for it, but technically it's not right. Okay, so y2 minus y1 over x2 minus x1, which gives us 0.4305 over 0.1, which is approximately 4.305. So at the point x equals 2, you can say that that curve, that cubic curve, for every increase of 1 unit in x, there is an increase of 4.305 units in y.
Is that again?
For every 1 unit increase of x, there is 4.305 units increase in y.
Say that again.
That's what gradient means. Like as you increase x by 1, y is being increased by that gradient number.
I didn't know it's the other way around.
Because like x is the independent variable, so it changes first and causes the y, the dependent variable, to change. That's it. Pretty straightforward.
Yeah, neat.
Okay.